Hello. So now we are going to discuss about the excitation table of JK flip-flop. I'll show you here how the excitation table of JK flip-flop is constructed or obtained or illustrated. So before designing or illustrating the excitation table of any types of flip-flop, we need to be well known about the characteristic table of those flip-flops. So here we are going to use JK flip-flop, you know. Um, so the characteristic table of JK flip-flop is here, which we have already discussed, or you might have discussed already in the portion of flip-flop. Again, let me remind you about the characteristic table of JK flip-flop, or let's say truth table of JK flip-flop. Here Qt is the present state and Qt plus 1 is the next state. Here you can see it, make sure about it. And when both inputs of flip-flop J and K do have the value as 0, then the Qt plus 1, that means next state will provide the value of Qt, which is the present state, that is no change condition occurs here. It means if the value of Qt is 1, then the value of Qt plus 1 will also be 1. If the value of Qt is 0, then the value of Qt plus 1 will also be 0 if both the values of J and K is 0. Okay, so now let me remind you once again, the J input works as the set input and the K input works as the reset input. We are well known about it. Now when the J input is 0 and K input is 1, then the Qt plus 1 will be 0, which is the reset condition. And when the J input is 1 and K input is 0, it provides it means Qt plus 1, or let's say next state, provides the value of 1, that is set condition. And when both the inputs do have the value as 1, then the Qt plus 1 will provide the value as Qt complement, that is toggle condition. It means complement of Qt. If Qt is 0, then Qt plus 1 will be 1. If Qt is 1, then Qt plus 1 will be 0, since it is the toggle condition, or it complements the value of Qt and provides the value of next state, that is Qt plus 1, as Qt complement. Okay, now after being familiar with characteristic table of JK flip-flop, we are going to construct the excitation table of JK flip-flop on the basis of this characteristic table of JK flip-flop. Now let's see how the characteristic table of JK flip-flop is constructed. Now let me show you. Okay, now I'm gonna show you here. Listen very carefully and observe very carefully. Okay, now at first let's compare these both states, means present state and next state, 0 1 0 1, here it is 0 0 1 1. Now on the basis of these present states and next states, we need to determine the value of flip-flop inputs, that is J and K in the case of JK flip-flop. Now let's watch both the states, that is present and next state, or Qt and Qt plus 1. Look at here, both the values are 0. Look at here, Qt is also 0 and Qt plus 1 is also 0. It means it is the no change condition. Look at here, if Qt plus 1 has the value of Qt, or similar value as that of Qt, then it is a no change condition. Look at here, Qt is 0 and Qt plus 1 is also 0. Here 0 is the value of Qt. It means it is a no change condition. Since present state, that is Qt and Qt plus 1, both have the same value, it is a no change condition. It means present state also have the value as 0, and next state has also the value as 0. It means it is a no change condition. So when there is a no change condition, the value of J and K is, here it is 0 0. Okay, here it is 0 0. Okay, first condition is 0 0. Now in the second scenario, let's observe only this next state. Okay, next state is 0, or the value of Qt plus 1 is 0. Let's see here the value of Qt plus 1 as 0. Here it is, see the blue color, you know, when the value of Qt plus 1 is 0, then the flip-flop inputs value is 0 and 1. Yeah, only see the next state. When the next state value is 0, then the flip-flop inputs do have the value as 0 and 1. It means the value of J input is 0 and the value of K input is 1. Yeah, 0 and 1. Okay, 0 and 1. Now let's go to the, for a bit while leave it as it is. Now let's go to the second state. Here it is 0 1. Now look at here, Qt is 0 and Qt plus 1 is 1. See, it is a toggle condition, or it is a complementing condition. See here, the value of qt is 0 and qt plus 1 is 1. It means the value of qt is complemented here. See, I mean it is toggled here. It means qt is toggled value. No, when qt plus 1 does have a toggled value, then the both inputs do have the value as 1. Yeah, 1 1. Since it is a toggle condition. Now in the second case, just observe the next state only. Okay, the next state value, the next state does have the value as 1. So I mean the qt plus 1 has the value as 1. Now when qt plus 1 has the value of 1, then the j and k flip-flop do have the value of 1 and 0. See, j possesses the value of 1 and k possesses the value of 0 when qt plus 1 is 1. I mean next state, qt plus 1 is 1. Okay, so when qt plus 1 is 1, then j and k does have the input as 1 and 0. 1 and 0. Okay, now let's move on to the next state, that is 1 0. Now let's again look at here, it is also a toggle condition. Look at here, the value of qt is 1 and the value of qt plus 1, which is next state, does have the value of 0. It means the value of qt, which is 1, is complemented here as 0. So it is also a toggle condition. That is toggle condition. When there is a toggle condition in qt plus 1, then the both the flip-flop inputs j and k does have the value as 1. Okay, now again in the next scenario, just observe it or look at the next state 0, that is qt plus 1. When here it is, see in the blue stripe here, qt plus 1 does have the, or next state does have the value of 0 when there is, when j does have the value of 0 and k does have the value of 1, that is 0 1. Yeah, 0 1. Now let's go to the next scenario, that is 1 1. Look at here, the value of qt is 1 and the value of qt plus 1 is also 1. It means whatever the present state poses the value, the next state is also possessing the same value. It means it is also a no change condition. Look at here, qt also possesses the value of 1 and qt plus 1 also possesses the value of 1. It means there is a no change condition. Whatever the present state qt is possessing the value, the same value the next state qt plus 1 is also possessing. It means it is a no change condition. It means qt plus 1 is having the value or as qt. It means qt means 1, which is the value of qt right here, 1. Qt does have the value of 1, and then same the value of qt1 is the value of qt plus 1. It is a no change condition, and when there is a no change condition in the next state or qt plus 1, then the both the inputs of jk flip-flop j and k does have the value as 0. Be sure about it. Okay, now in the next scenario, just look at the next state. Okay, now the next state is 1. Now when, look at here, it is, look at the, in the yellow stripe, it is the qt plus 1 does have the value of 1 when the j input of jk flip-flop does have the value of 1 and k input of jk flip-flop does have the value of 0. Yeah, when there is the when 1 is the value of next state qt plus 1, then the flip-flop inputs j and k will have the respective values of 1 and 0 for j k flip-flops. It means it is 1 0. It is very simple, it is very simple case. Okay, now yet the excitation table of jk flip-flop has not been completed. Okay, look at here, for a simple understanding, let us make a mindset that the present state here is possessing a single value, so that so as that of next state is also possessing this single value, but the flip-flop input j and k are possessing the dual values in the same state. Look at here, in the 0 0, it means in the same single state, Z and K flip-flop inputs are possessing the 12 values, which is incompatible to this mechanism. So to make it compatible or more familiar or more reduced or modified excitation table of JK flip-flop, we're gonna modify this in this way. Look at it now. Let us analyze in this way. When the present state is 0 and the next state is 0, then the value of J input is always 0. Look at here. In the both case, the value of J is 0. In both the cases, the value of J is 0. Whenever the present state is 0 and the next state is also 0, then the J input of JK flip-flop will always possess the value of 0. And when the present state is 0 and the next state is also 0, the K input of JK flip-flop can have either the value as 0 or can have either the value as 1. It means 0 or 1 both can be suited in the case of K input. So we can write it as, it means J is always 0, means J is always 0. So now for K input, we do not consider whether it is 0 or 1. We can define K as 0 also. We can define it K as 1 as well. So we do not mention K as 0 or 1, or I mean we do not mention means we cannot mention K particularly as 0 or particularly as 1. It means it does have indistinct value. It can have either 0 or it can have either 1. So it does not matter us whether it has 0 or 1 value. So we possess it as a don't care condition. Okay, because it doesn't matter whether the K input has 0 value or 1 value. It is a don't care condition. Now after this scenario, now let us go to the state 0 1. Okay, now whenever the present state is 0 and the next state is 1, the J input of JK flip-flop is always 1. Look at these two scenario. Look at here, 1 1. Both the values, both the scenario poses the value of 1 for J input of the JK flip-flop, but the K flip-flop is fluctuating between 0 and 1. The K input of JK flip-flop can have either 1 or 0 during the state transition of present state of 0 to next state of 1. So in this case we can modify this as a single 1 for 1, and it doesn't matter whether the K input does have the value of 1 or 0. It doesn't matter, so it is the condition of don't care. Okay, now for this state next 1 0, when the present state is 1 and the next state is 0, the K input of JK flip-flop will always provide the value of 1, and J input is fluctuating in between the value of 1 and 0. It means the J input can have either the value of 1 or can have the input as the 0. It means both values are possible, so it doesn't matter whether it has 1 or it has 0. So it can be written as it as a single 1, and it doesn't matter whether it is 1 or 0. So here it is a don't care condition. Now in the same way for the present state 1 and the next state 1, the K input of JK flip-flop is always 0, and the J input of JK flip-flop is fluctuating in between the value of 0 and 1. It means J input can have either the value of 1 or I can have the value of 0. So it doesn't matter whether it has the value of 1 or 0. So it is a don't care condition. So it is K flip-flop always possesses the value of 0, and it doesn't matter whether the J input provides 1 or 0. So it is a don't care condition. It can have either 0 or 1 as the value. So finally this is the final excitation table of JK flip-flop which we have to construct. Okay, so for your better understanding, you can construct the previous state table which I had constructed this before, where I had passed two values 0 0 and 1 0. You can construct that, and you can write down there. Further we can modify this excitation table as follows, and you can finally get this excitation table. So this is the actual excitation table of JK flip-flop. I hope you get it, and you will be well clear about the construction of excitation table or illustration of excitation table of JK flip-flop. Now on the basis of this excitation table of JK flip-flop, we can understand the mechanism of circuit excitation table of 3-bit synchronous binary counter. Okay, now the 3-bit binary counter will have the three states, that is Q2, Qn, and Q0, where Q2 is the most significant bit MSB and Q0 is the least significant bit LSB. Okay, so the next state also has the states as Q2, Q1, and Q0. I already mentioned you that you can state them as Qt plus or Q1 plus or Q0 plus as per your choice. Here I have designated the next state as that similar of the present state. Okay, now the present state is 0 0, then its next state is 0 0 1. And so if the present state is 0 0 1, then its next state is 0 1 0, and finally when we reach triple 1, then its next state is triple 0. We can see it from the state diagram from here. So look at here, the present state is, if the present is 0 0, then its next state is 0 0 1. In this way, when we reach this state triple 1, then it recycles back to the initial state, that is triple 0, which is the binary value of the decimal 0, and triple 1 is the binary value of the decimal 7. We are well known about this. So now after the construction of present state and next state, now we're gonna find out the value of flip-flop inputs. Okay, now let's find out the flip-flop inputs Z2, K2, J1, K1, and Z0, K0. Here Z2, K2 is the are the flip-flop inputs for the present state Q2 and the next state Q2. Here J1, K1 are the flip-flop inputs for the present state Q1 and next state Q1, and Z0, K0 flip-flop in are the inputs. Are the flip-flop inputs for the next present state Q0 and the next state Q0. Okay, now let's construct the circuit excitation table. Now when the present state is 0, now let's look at only toward the Q2, Q2. Okay, let's match Q2 and Q2 only. Now when the present state of Q2 is 0 and the next state of Q2 is 0, what happens? Now let's see here the excitation table. When the present state is 0, Qt is 0, and the next state Qt plus 1 is 0, then the flip-flop inputs will be 0 and don't care. So when the present state is of Qt is 0 and the next state of Qt is 0, then the J2 K2 will be 0 and don't care as per the excitation table of JK flip-flop. Now again let's see, when the Q2 state has the value of 0 and the next state of Q2 has 0, then when 0 is the present state of Q2 and 0 is the next state of Q2, it also poses the same 0 and don't care flip-flop inputs. Okay, as it's same scenario of the first state. If it is here 0, then the next state is also 0, then the flip-flop inputs will provide the value of 0 and don't care. In the same way, when the present state of Q2 is 0 and the next state of Q2 is also 0, then the flip-flop inputs is going to provide the value as 0 and don't care. Now in the third state, let's go. When the present state of Q2 is 0 and the next state of Q2 is 0, it also provides the value of J2 and K2 as 0 and don't care, as similar that to of previous two states 0, 0 0 and 0 0. Okay, now in the let's go into the fourth state. When the present state of Q2 is 0 and the next state of Q2 is 1. Okay, 0 and 1. Let's see what happens when 0 0 1. Let's see in the blue stripe. When the present state Qt is 0 and the next state Qt plus 1 is 1, then the flip-flop inputs gonna have the value as 1 and don't care. So when the present state is 1, sorry, when the present state is 0 and the next state of Q2 is 1, then the flip-flop inputs will have the value as 1 and don't care. Okay, now in the next state, when the value of Q2 present state of Q2 is 1 and the next state of Q2 is 1, now let's see what happens. When the present state is 1 and next state is 1, then the flip-flop inputs will provide the value as don't care and 0. Okay, when the present state is 1 and the next state is 1, then the flip-flop is gonna provide the output as don't care and 0. Similarly, you can find out yourself, match the present state of Q1 with the next state of Q1 and write the flip-flop operation in J1 and K1. Similarly, go to the Q0 of present state and Q0 of next state and match those values and see the excitation table of JK flip-flop and write this in flip-flop inputs value in J0 K0. In this way you can consider, in this way the circuit excitation table of 3-bit binary counter is constructed right here, and on the basis of these of this circuit excitation table, the K-map simplification is obtained right here, which I've already discussed previously and in the previous class. So you can construct here the K-map construction is done here, a simplification method is carried out, and after, on the basis of this K-map simplification method, the final circuit of 3-bit synchronous binary counter is constructed right here. You can see in the expression the J naught and K naught are getting the value as 1, which is high, or you can write here or logic 1. And similarly the J1 and K1 inputs of flip-flop FF1 are getting the input from the output of FF, the first flip-flop 0, that is Q naught. And as per the K map, you can see the J2 and K2 flip-flop inputs of flip-flop 2 are getting the inputs from the AND operation of output of flip-flop 0 and flip-flop output of flip-flop 1, that is Q naught and Q1. You can see in the K map, look at here, J2 also gains the input as Q1 and Q naught. Here K2 also gains the input as Q1 and Q naught. It means AND operator is used here, which is illustrated by the AND gate. So this is the final circuit. I hope you guys uh, will get it. And so never mind with my language. So I'm not a I'm not very proper English speaking person. I have not got a good speaking tone, English speaking tone. I'm not perfect in English speaking. I might have made many mistakes in speaking English. So beside laughing in my English, please focus on the content and don't forget to like, comment, and subscribe, and press the bell icon for further notifications. I must say, because YouTube is also a past thing, as you have already known about it. So thank you. If you have any confusion, please post them in the comment section so that I can be updated and I can keep you as well, and I can keep you too updated. Okay, so let's be updated and let others be updated. Thank you.